Good afternoon. How are you doing? Hello, Jack. Hello, Trogdor. Hello, Nookis. Pretty good? It's Friday. It is Friday. I'm doing pretty good too. Friday. I'm glad it's Friday. I've had a good week. But I could use a little rest too, as I'm sure you guys could. Hey D Stratus, good morning. Good morning, Squared Circle. And Pika Pika, my man. Happy Friday to all of you guys. Afternoon, Shrek. Happy Friday, Belkit. Is it just me, or is time flying? It is. Because this is the end of week 3. And if we only have 15 weeks, 15 straight weeks, that means we're a fifth of the way through. Hey JP, Pika Pika, will Homework 2 be released soon? Yes. It's going to be up this weekend. It's a little later than I wanted it to be, but that's okay. Hey Brandon. That was brutal on Wednesday. You destroyed me in chess. Ruthless. Sorry about that. You're not sorry. Not sorry. I know. Hope it doesn't affect my grade. Well, you shouldn't have made your Twitch chat name your actual name. You should have been like a Squirtle engineer or something. Turns with zeros don't show weakness. The correct response is GG easy. There you go. That's true. Hello, Amin. Okay, let's get started. Happy Friday, Mike. What is up, Kate? Hello. Happy Friday to everyone. All right, so we've been talking about what do you do in your free time, Dr. E? Depends. Right, like this summer, I've been enjoying reading, and recently Nintendo Switch. I'm playing Breath of the Wild. We can talk more about that later. But I'm reading the Stormlight Archive. Do you guys know that? Man, I'm enjoying those books. They're by Brandon Sanderson. Okay. Let's do this. Okay, so we're talking about rise time. We're looking at like a second order step response here. And it looks something like this. And this is kind of just, like I said, it's our convention for describing how a control system responds to a reference. Because you could respond to a step reference in many different ways, like maybe you slowly approach, maybe you overshoot like this. So we need a language to be very specific about how we want our control system to follow something. So the rise time is one of these specifications, and this is, let's see, do I have the definition? Okay, yeah, we're going to write it out. The time it takes for the response to pass through the final value for the first time. So in other words, like your response might hit that steady state value and then hit it a couple times again. That could definitely happen. So the rise time is how much time it takes to reach that value for the first time. So that means if we call that response X, if we evaluate it at the rise time, it should be equal to 1 if the example we've been looking at, the steady state value is 1. And this is the equation. So every time that there was the time variable, I substituted in the rise time. All right, so we're going to do some manipulation of this and solve for what that time is. And it gets a little bit tricky. It took me some time to get to the bottom of this and be satisfied with the answer. But like if you subtract this 1 on both sides, then you're going to be left with, so I'm going to skip some steps here, but you're going to be left with this expression, this exponential times this trig function. You're going to be left with that is equal to 0. And there's a couple ways that can happen. Like either this term could go to 0, but that only happens when time approaches infinity. But we're looking for a time much earlier. It's like the first time that we cross the steady state value. So all that we're left with is that this expression has to be equal to 0. So we're going to write that out. The damped natural frequency times the rise time, damping ratio, 1 minus damping ratio squared, sine of that thing. So the sum of these functions has to go to 0. Okay, we're going to divide this by cosine omega dtr. So this cosine term, you're going to divide that by cosine. It's going to go to 1. This sine is going to be divided by cosine, so that term is going to go to tangent, and then we just have this coefficient out in front. Z squared. So tangent omega dtr equals 0. Okay, and this tangent is what's going to make this a little bit tricky. So let's isolate for it. It's going to be negative square root 1 minus damping ratio squared over our damping ratio. And then if we solve for the rise time from this, it's going to be 1 over our damped natural frequency times the inverse tangent of this negative thing. Okay, so like I said, this is where it gets tricky. Because if you just plug this expression into MATLAB, you're going to get something that doesn't make sense. It won't be the rise time that you want. Where'd the 1 go? Oh, okay, because the one, I moved it over here, and so then I just have negative 1 is equal to this stuff. And that -1 is why we have like this negative here. Okay, so we have to note 3 things, because this is where it gets tricky. Number 1, the inverse tangent function, by convention, is restricted to return values between minus pi over 2 and pi over 2. Like, you might not have thought about the inverse tangent function in a little while, but you probably know in the back of your mind there's something tricky about it. Tangent's a little tricky. Like, if you plot tangent like as a function of like theta or something, it looks like this. A tan 2 time. Maybe I don't use A tan 2 for this, but it's the tangent's tricky, right? Okay, so it at pi over 2 and minus pi over 2, those are like asymptotes where it goes up to infinity or negative infinity here, and then we know that it repeats. So this is why the inverse tangent is tricky, because the goal of the inverse tangent is you give me like a value of the tangent function, so maybe this number up here, and then the inverse tangent tracks it back down to the angle that corresponds to. But you see that because this thing repeats, there's actually many different angles, infinitely many, that you could return to me. So that's why in order to be a function, you have to return one value. And so that's why they said, hey, let's just make an agreement among people that we're going to return the value between minus pi over 2 and pi over 2. So just when you use inverse tangent, this is usually the convention. So MATLAB's going to give you that. So that's the first thing to note. The other thing to note is that the rise time must be greater than 0. Like, it can't be negative. We can't get a negative rise time. And the third thing is that the rise time must occur at the first time the signal crosses the steady state value. So we're looking for this one right here. We're not looking for this or this or this. Okay, so those 3 things we need. So this one is the rise time. This amplitude is the steady state value. Okay, so we're going to break this down now. Let's consider graphically this tangent of a negative number. And this is one way to do it. Like, you know that when we're calculating the tangent of some angle, if the side lengths are like x and y, then tangent of theta would be the ratio of y over x. So I'm kind of looking at this function in this way. Let's see, maybe, yeah, I'm using this as like the y value. I'm using this as the x value. And really, you could interpret this in different ways because you have this negative sign. So what I have is I have like negative zeta. I'm thinking of that as the x value. I'm assuming that the negative sign went to that. And this is just my y value. So this distance here is square root 1 minus zeta squared. The distance here is zeta. That's just the amplitude. That's why I'm not putting a negative sign. Okay, but then there's another option. You could assume that the negative sign corresponds to like this y value this time. and then we're leaving the x value positive. So this actually makes a point over here. And these ratios are the same, like the amplitude here is still zeta, and this amplitude is still 1 minus zeta squared. But let's think about the angles that these two interpretations make. So this one, let's call this theta 1. Let's define the angles relative to the positive real axis going counterclockwise. So like this one, I'm going to call this theta 2, but I'm going to go this way. Okay, so there's different possibilities. And then if you add pi to each of these angles, that's showing like the infinite number of possibilities that this inverse tangent could return. But by convention, the inverse tangent is going to pick, it's restricted between minus pi over 2 and pi over 2. So here's what's going to happen. When I run the inverse tangent of this ratio, it's going to return theta 2. Because theta 2, you could find a representation for it that's within the pi over 2 to minus pi over 2 restriction. You know, because over here is like to pi over 2. This is the angle to minus pi over 2. So anyways, the inverse tangent, it's going to give this angle right here, and I didn't make up a variable for it for some reason. Okay, but we'll just continue with this. It's going to return that angle because it has an equivalent representation within that restriction. But we're going to get a negative angle. And then the rise time will be negative. Because if you look at our rise time formula, wherever that went, way up here, it's 1 over omega d times this. And so I'm telling you, this is going to return a negative number. So that's not good. Okay. If we convert theta 2 to its positive angle representation, so I know that this orange angle is going to be returned because of the restriction, but what if I just convert this to this blue theta 2? So now it's positive. But if I do that, it'll be greater than theta 1. And this positive theta 2 will actually represent the second time the signal crosses the steady state value. So, okay, here's the point. We actually want theta 1 for our rise time calculation. But the inverse tangent formula gives us the negative representation of theta 2. So we have to be able to know that we're given theta 2, but convert it to theta 1. So if you look at this picture, theta 1, this angle, let's just make a name for this. I don't know, theta 2 hat. It's some negative number. So if I'm given this, then theta 1 is theta 2 hat plus pi. So that'll make it positive, and it'll make it this angle. Okay, so I'm going to write that down here. Theta 2. Sorry, I know it's a little weird that I'm using like a hat variable now. So, to correct our rise time formula dealing with this arctangent issue, we're gonna change it up a little bit. Like it used to just be this. It has the tangent inverse of this negative square root of 1 minus zeta squared over zeta. Now we're gonna add pi. Because that's gonna give us the angle we want. And then you can rewrite this in a slightly more convenient form. I think it looks a little better. You can do pi. And then you can bring the negative sign outside of the tangent. And that's the formula we like to use. And I see I just got a follow for this channel from that guy who does not stink. Wow. Now we have the pair. The person who stinks and the person who does not stink. Okay, show yourself! That's funny. Okay, let's do some examples. Let's bring it all together. Examples help to bring it all together. All right. So this example, our goal is determine the second order continuous system roots that characterize this noisy step response below. So this is like what a system response might look like if we monitor it with some sensors. And so what I want to do, I want to find the second order continuous system that kind of represents this behavior. So let's just start by pointing out a few things. You can see that it looks like as time is going towards infinity, the limit of this function is around 3. Oh, nice. Okay. So if we let's superimpose that steady state value on here. I'm just going to like draw a line through it. I know we don't have LED orange. You're gonna have to use like red or yellow or blue. Okay, let's do the overshoot. That's easy to get. So this happens at the first peak. The definition is you take the height of this peak, which I'm going to say it's around 4.5. You subtract the steady state value and then divide it by that steady state value. So this is an overshoot of 0.5, or you could call it 50% overshoot. Let's look at the rise time. So that's the time it takes to get to like this first crossing. And it's with the tick marks here, it's kind of hard to tell, but we're just going to say, that looks like it's around 0.8 seconds or so. Because each of these tick marks, this is 2 seconds. It's a little less than the halfway point. All right. We can also get the damped period of oscillation, meaning how much time it takes to go from peak to peak here. So like from that peak to this peak. Or you could pick the negative peak. So we have this distance. And there you go. So I'll call this the T sub D around 3 seconds. So this is called the damped period of oscillation. So right now we're just pointing out a bunch of different features of this. Settling time is one of our performance characteristics. And this is why this is actually the reason I made the signal noisy. I wanted to make a point. It's very hard to determine settling time precisely from a measured signal, especially with noise. Because remember, the settling time is when the envelope gets to within 2% of the final value. But you can see that the amplitude of the noise is consistent everywhere. But once the amplitude of the signal about the steady state value becomes small, so like the oscillations here are kind of small amplitude, the signal to noise ratio is huge. Like the noise is greater than the amplitude of the signal itself right there about the steady state value. So it's kind of impossible to determine when you get within 2% because it's so fuzzy around here. So like I'm going to guess, I'm just eyeballing it. Maybe the settling time is around 8 seconds, okay? So it's hard to tell with the noise. All right, so we're gonna try to characterize the system that generated this. So remember, the steps are like just making a little flow chart over here. First, we want to determine the damping ratio and the natural frequency. That's like the first step. Then the second step, we convert these to continuous roots, which are a function of those two quantities. So that's for an underdamped system. And then later we're going to convert these to discrete roots using this relationship. E to the continuous root, the product of the continuous root and the sampling period, whatever that may be. But right now we're focusing on this, and particularly we need to get those two quantities first. So the way I like to start, the overshoot directly gives you the damping ratio pretty reliably, and we know that the damping ratio in this case is around 0.5. So this is the formula that relates the damping ratio to the overshoot. And if you calculate this, right off the bat, we know that the damping ratio is somewhere around 0.215. All right. The other thing that we can judge reliably is that damped period. So the distance between successive peaks. If you have an underdamped system, I think that's going to be pretty easy to tell, like what that frequency of oscillation is. So we said it was around 3 seconds. So the damped natural frequency is related to that damped period of oscillation by this relationship. So we're going to have 2 pi over 3 radians per second. Or if you want to convert that, 2.094 radians per second. Okay, and then, so we need the natural frequency. That's different than the damped natural frequency. But we know that the natural frequency is related to the damped natural frequency by this formula. So that means the natural frequency is just omega d divided by the square root of 1 minus zeta squared. So if we plug in those numbers, we're going to have 2.094 radians per second over the square root of 1 minus 0.215 squared. And this number in the bottom is going to be pretty close to 1. So usually the damped natural frequency and the natural frequency are pretty close. So we got 2.144 radians per second for the natural frequency. So compare that up above to the damped natural frequency. The natural frequency will always be a little bit higher. Oh, we got another follow from Prison Mike Michael. Very nice. The Office. Fans of The Office. Okay. So we have a natural frequency estimate. We also have a damping ratio estimate. And we use the overshoot and the damped period to get those. We could have used other quantities like the rise time, the settling time, but those are a little less reliable. Like the rise time, you could probably pretty accurately get that. But because of the tick marks here, whatever, we couldn't really eyeball it. And then the settling time is just very hard to determine. But let's calculate those using the quantities that we just got from the other more reliable numbers. So we know the settling time is approximately equal to this. The product of the damping ratio and the natural frequency in the denominator. So we got 4 over 0.215 times 2.144. And this is going to give us 8.675 seconds. So I can go back to the figure and double check, does this seem reasonable? So 8.675 seconds, is that when I'm within 2%? Yeah, that looks pretty darn reasonable. And we thought just by eyeballing it, it should be around 8 seconds or something. Is that the same formula we used in MAE 340? Yes, it is. Great question. Okay, and the rise time, let's use that massive formula we derived up above. But I just want to show you that this works pretty well. Over zeta, and this, we added that modification, we added in that pi to make sure the tangent gives us what we need. So if you just run this into MATLAB directly, you're going to get 0.854 seconds. And if you look at the figure again, that's pretty darn consistent with what we saw. So all of these variables, these quantities are related to each other. So just from inspecting the graph, I know that the continuous time roots of this system must be close to, so this is these are what the roots are going to be for an underdamped second order system. And we're going to get minus 0.461 plus or minus 2.094i. Okay, now the gold standard to see if these roots really correspond to the system we were looking at is to design a differential equation that has these roots and then get the step response and see if the response is the same. You're here for some culture. This is the seat of culture in global society, so you're in the right place. Okay, so that's what we're going to do, but we're going to do it in discrete time. All right, so we've done steps 1 and 2. Now we're going to talk about step 3. Let's make a discrete system that behaves like this. Okay, so this brings us to the next example. We want to create a discrete time system that mimics this behavior. But let's assume that the sampling rate is 2 hertz. So we're only updating the system 2 times per second, or every half a second. I want to provide a difference equation that describes that system we saw up in the figure. Okay, so the first step, we know the conversion from a continuous time root to a discrete time root. We have this formula, which is pure gold. So t is the sampling period, so t is 1 over that sampling frequency up above, so it's 1/2, 0.5 seconds. All right, now for complex conjugate roots, you can expand this out. This will be the real part of the root. So we can take all those quantities we found up above, substitute them into this expression. That's going to be the real part of our discrete time root. And then the imaginary part is the same thing, just with a sign. All right. Okay, t is 0.5, damping ratio 0.215, natural frequency 2.144 radians per second, damped natural frequency 2.094 radians per second. So just bringing them all into one place. And this is what you're going to get. 0.3972 plus or minus 0.6877i. So these are the discrete time roots. If we update this system every half a second, it should behave similarly to that signal up above. So if we make a difference equation whose characteristic equation has these roots, it should behave similarly. Okay, how do you get a difference equation from a pair of roots? So I like to make problems like this where you have to work backwards. Like a lot of the problems that we do, like we start with a difference equation, we derive the characteristic equation, then we get the roots. I would call that like the forward direction. How do you go backwards? How do we get a characteristic equation? Okay. This is the fundamental way to do it. Multiply them. Something like that. We know that those roots up above satisfy some equation. So, okay, so if I subtract, I'm going to plug in these roots, 0.3972 plus 0.6877. Hard to put into words in the chat. Yeah, I know. Yeah, it's a challenge. I have the luxury of speaking into the microphone and I'm struggling to find the words for it. So I'm going to write this out first. Okay, remember, what does it mean to be a root of a polynomial? Well, like the characteristic equation is some polynomial. Well, it's hard to see the polynomial here right now, but it's some polynomial equal to 0. And when we solve that equation for the roots, we know that the roots are equal to these numbers. So if I were to plug in one of these two roots for this lambda d variable, this equation just goes to 0, right? Like if I take this same number and I plug it in right here, I'll have the same number minus that same number, it goes to 0. So that is a solution of this equation. So if you multiply this out, like if you distribute everything, you're going to see it's going to turn into a polynomial gradually, slowly but surely. 3972 minus, like all these imaginary parts are going to cancel out. Minus 0.3972 plus times lambda d. Like already in here, this cancels with this. And then we have one more line of this thing. 72 plus 0.6877i minus 0.3972 minus 0.6877i. So this is the same equation up above. I just expanded that all out. If you multiply it out, this is what you get. Lambda d squared. So now it's just a pretty little polynomial. 0.6307. And all the numbers are real. So if you were to now calculate the roots of this, substitute into the quadratic formula, whatever, you're going to find out that the roots are equal to these numbers up here. Okay, so now we have the characteristic equation. How do we convert this to a difference equation? We have to do another step of going backwards in time. Do you remember how we started from the difference equation and converted it to the characteristic equation? Okay, the first step, multiply the characteristic equation by some scalar a times lambda d to the k minus 2. So you'll see what happens when I do this. Okay, this is going to become a times lambda d to the k. Because like if you multiply lambda d to the k minus 2 times lambda d, the positive 2 and the minus 2, they cancel, and you're just left with lambda d to the k. And then this one is going to be minus 0.7944 lambda d to the k minus 1. Oh wait, I missed my a. We got to put an a in front. And then the last term, 0.6307, this one's easy. It's just times a lambda d to the k minus 2, and that equals 0. Now remember, we define the homogeneous solution of a difference equation with this general form. X at step k is that constant a, whatever it is, times lambda d to the k. Now I know I'm going through this kind of fast, but when you, I think you guys are pretty fast at going through this in the forward direction. If you try it from this direction a couple times, it'll make sense. So, you can see this term right here is already the same as this. So the first term should be xk, and then I have minus 0.7944 xk minus 1, because xk minus 1 is just a times lambda d to the k minus 1, and so on. So plus 0.6307 x to the k minus 2. So if you were to calculate the characteristic equation of this difference equation, you're going to get that. And actually that makes a lot of sense. If you just compare those two lines, you'll probably just skip between those, because it's real easy to kind of see that pattern. All right, and then you can get, like, we kind of like to write it in this standard way. You bring the xk over to one side. So we'll bring these terms over to the right-hand side by subtracting them. Okay, but this is just the homogeneous form of the difference equation. So, like, if I give it some initial condition, every 0.5 seconds, oh, I don't know exactly what it looks like, but it's gonna kind of like oscillate, but it's not gonna behave like that step response that we had earlier, where it goes from 0 up to 1. You need some external excitation to drive it away from 0. Okay, so how do we model the step response of this discrete time system? Because, like, right now, it's just the homogeneous form. So, unfortunately, I wish it was different than this. It's not as simple as just adding a constant to the right-hand side of the equation. Like, we know if you have a differential equation, I'm just going to make up some second-order one. If I want to get the step response of this, I can just add a constant to the right-hand side of the equation. That's how you get the step response of a differential equation. So I wish that I could tell you whatever our differential equation is, I mean our difference equation. I wish it was as simple as, like, you just put a constant on the right-hand side. And actually, I thought it was that for a while. It's a little embarrassing. It's close. It's close to this, but it's not exactly that. So we want to be precise. So for now, I'm just going to show you the result, because I can't give you the explanation, the best explanation right now of why it looks the way that I'm going to show you. So later we're going to discuss exactly how to get it. Okay, so first, we're going to define our input like this. At every step k, we're going to have an input u. And because we're doing a step input, actually, I'm just going to make it a unit step input. I'm going to say that it's always going to be 1 for all values of k that are greater than or equal to 0. So that upside down A just means for all. So if you pick any value of k in the sequence greater than or equal to 0, this is going to be equal to 1. So it's just a Heaviside function where it's 0 and then suddenly we turn it to 1. But it's discrete. It only exists at those points. So I'm going to take this same difference equation right here, but I'm going to add a couple terms. Okay, 0.7944 xk minus 1 minus 0.6307 xk minus 2. Okay, that's what we had before. So now we're going to add these two terms. And right now I don't have the best explanation. We will explain it. And for all of these, they're going to follow this definition up above. They're just going to be equal to 1 depending on what the value is. So if you plot this recursive solution and you make like a for loop, you're going to see that it does behave very close to that original system. You can kind of see each of these discrete points is overlapping. So this one is x at 0. So we call that x step 0. This one is x at our first sampling point, which is when t is equal to capital T, which was at 0.5 seconds, and we call this x1, x2, x3, x4, so on. And you see that all these points are separated by 0.5 second intervals. So the big picture important thing of this is when we design a control system, remember the first step is you visualize in your mind, what do I want the system response to look like? Do I want it to oscillate? Do I want it maybe to have less overshoot? Do I want it to have a very quick rise time and level out? As the control system engineer, that's the first thing that you think of. And now, with some of these performance specifications that we defined, you're going to be able to make first a continuous system that behaves in the way that you visualized in your mind. So it's something abstract. It's not something real yet. Then you're going to be confronted with reality. You're going to be using some Arduino, and when you start programming, you're like, wow, I'm only getting 50 samples per second. Maybe I'm getting 100 samples per second, something like that. Or your boss is like, we're going to get the cheapest microcontroller we can find, and you're going to get 10 samples per second. The good news is that you're going to be able to design a system with whatever spacing in between these points there is, but it's still going to be able to behave generally in the way that you conceived of. And if you just used a continuous system controller for some of these slower sampling times, it's not going to work. Because these slower sampling times really jack up the whole thing. But that's the great thing about digital controls. The sampling time, we can work with it. We can work with it. And that's it for today. We went through the examples. So the next homework, that's going to be up this weekend. It's going to be doing this kind of stuff. Conceiving of systems that do certain things. And then making difference equations that describe that same thing with different sampling rates. I know I blasted you with a lot of information today. Can you show the boxed X? Yeah. You're welcome. You're welcome. Will we need an Arduino for this class? No. But I am going to have you design a controller for a motor, and I'm going to use an Arduino to control that motor, but you're going to give me the control law. And then we'll be able to test your control law on the hardware, and you'll see if your controller works. Will you upload these notes, please? Yes. They're ready to go. I'm going to put them up. So you're gonna design one of these. Can we use our Arduino just because it's cool? Yes. I guess I'll see you all on Discord this weekend. Yeah. That's the place to be. Good. I'm taking MAE Lab 1 now. Will I be missing anything? You're not gonna... What would you be missing? What are you talking about? Oh, I see. So you have the kit. Do you have everything you need in the kit? Okay, that... I see what you... Oh, is there something I need to know from that class for this class? No. No, you're safe. I won't require you in this class to know Arduino programming. Even though, after taking this class, I think you're going to be very capable to make your own controller on an Arduino. Because like I said, the coding is basically as straightforward as adding, you know, a difference equation in there where you're going to say, hey, my input is equal to, and the equation will look something like this. It'll be some summation of terms you're getting from your sensors and something like that. Yeah, this class might help you. I think it definitely will enrich your understanding of MAE Lab 1. Speaking of MAE Lab 1, that lecture's coming up at 1:50 in a little over 10 minutes. So what I'm going to do, I'm going to end this stream right here, just so there's a break in the video. I'm going to get a little snack. Am I going to show the coding when I run the controller? Yes. And I'm going to give you the code as well. So like if you want to load it up on your own Arduino, you can do that. Hey, have a great weekend, Kate. Off-worlder, have a great weekend, Mike. I mean, we didn't get to build our sorting machine last year. I know. That was very sad. Hey, thank you, Trogdor, Brandon. See you, that guy who stinks, and also that guy who doesn't stink. See you, Amin. KT Feeney, Brandon, Pika Pika Pika. Bye-bye. Have a nice weekend, everybody. Get some rest. Have a great weekend, D-Stratus. See you Monday, Belka. I'll be looking around town for, yeah, there's some bad blood. Some bad blood. Oh, man. Wouldn't want to be, I know, that sounds brutal. Is the homework coming this weekend? That's right. It's going to be up this weekend at some point. Is the homework going to be due on a Monday? I'm not sure yet. It depends on exactly when I upload it. Casper, see you in MAE Lab. Yep. All right, it's always a pleasure. See you guys.